So far, this film has stressed conditioning and the control of operant behavior by reinforcing stimuli. Now we shall examine some of the other kinds of stimuli that control behavior. Behavior that has been conditioned in one stimulus situation is likely to occur in other situations. This is the phenomenon called generalization. This pigeon has been trained to peck this black circular disc. The pattern changes, and changes again. Because he responds, we can say that he generalizes to patterns of different hues. He continues to peck even though the shape of the pattern is changed. And the size. Nor does the number of stimuli presented alter his response. This bird, then, which was trained to peck a black circle, has generalized the pecking response to patterns that differ in hue, shape, size, and number. This would be a very difficult world to live in if there were no generalization. But it would be completely chaotic if there were nothing but generalization, if any behavior were likely to occur at any time or place. Usually a given response occurs more frequently in some situations than in others. We might hope that digging would occur more frequently in the sandbox than in the garden. When an organism responds differently in different stimulus situations, we say that he discriminates between the situations. The child does not yet seem to discriminate a sandbox from a garden. We can say that an organism is capable of a particular discrimination only if we can observe a differential response. We can say that this pigeon discriminates red from black only if we can get him to respond differently to red and to black. A person might respond differentially by naming the colors, but the pigeon will peck at a different rate. A discrimination can be established by a procedure called differential reinforcement. Behavior is reinforced differently in different situations. Here, pecking is reinforced when the pattern is red. Starting now, pecking is not reinforced when the pattern is black. If this procedure of differential reinforcement results in a differential response, if the bird pecks the red disc more often than the black, we can say that a discrimination has been established. In this case, we will determine whether or not pigeons can discriminate red from black. The clock was started when discrimination training began. The red and the black patterns are being presented for intervals of 30 seconds. We will plot the number of responses emitted during each of these intervals for each color. The cumulative response records will show whether or not there is a differential response, and thereby show whether or not the pigeon is discriminating red from black. Please note that we do not have to use punishment. We simply reinforce pecking the red disc and extinguish pecking the black. It is most important that the stimuli in a discrimination experiment differ in only one dimension. If these red and black patterns were of a different size or shape, then we would not know which aspect of the stimuli the bird was discriminating. As it is, we cannot say from this particular demonstration that pigeons have color vision, because the stimuli differ markedly in brightness as well as in hue. The bird could be responding to the lighter stimulus rather than the darker one. However, we could show by these same methods that pigeons do have excellent color vision. The stimulus present when behavior is reinforced is called an SD. The stimulus present when behavior is not reinforced is called an S delta. We cannot call a stimulus an SD or an S delta until we have a differential response. So we could not label these cumulative response curves until now, when we clearly have a differential response to black and red. Sometimes a pattern is presented for 2 consecutive intervals. This is to ensure that the bird is discriminating a difference in the stimuli and not just the alternation of reinforcement intervals. Since this is clearly a differential response, we can say that a discrimination has been established. Discrimination training is one of the ways in which we measure the sensory capacities of animals. If the experimenter can get a differential response in the presence of different stimuli, he can say that the animal is capable of that particular discrimination. For a human subject, the differential response may be verbal, or it may be some simple behavior such as pressing telegraph keys. Here, pressing the keys defines a vernier discrimination of offset, whether the lower black plate is offset to the left or to the right of the upper plate. Reading a slide rule requires a more familiar form of a vernier discrimination. In this experiment, judgments were made from a distance of 80 feet. At this distance, people with good vision can discriminate an offset of only 1/32 of an inch, most of the time. You might define reading as the ability to emit an appropriate differential response to written commands. On the other hand, if you saw a pigeon do this, you might not. Originally, this was a hue discrimination. The word peck was printed in red and the word turn in black. We gradually blackened the letters of peck as discrimination training proceeded. Actually, pigeons are capable of good pattern discrimination, and we could probably have gotten this discrimination by starting with all the letters the same color, even though the words are the same length. This performance was established by 2 undergraduates in approximately 5 hours. An SD is a stimulus in the presence of which some behavior is likely to occur. An SD does not stand alone. It is a discriminative stimulus for some specific behavior. These letters are an SD for the behavior of pecking, and these for the behavior of turning a circle. When people train their dogs, the commands, or SDs, are usually verbal. Here is an example of visual SDs in obedience training. These hand signals are the SDs for the dog to lie down, sit up, come and sit in front of his owner, and go around to her side and sit. Originally, each response was reinforced immediately. Now that the dog discriminates all the SDs, he is praised only at the end of the sequence. We will now see the complete obedience routine. The hand signal for forward is the first SD. When the handler stops, the dog must stop and sit at her side. Punishment was not used during any stage of the training. Both these dogs are pets, trained by their owners. The owner's behavior, in turn, is controlled by SDs from a judge who tells her exactly when to execute each maneuver.
Hey, Nick. Hey, Nick. Attaboy. Attaboy, Nick. Attaboy. Good boy. That's right. Good Nick.
SDs need not be auditory or visual. Many of the SDs in writing are tactual or kinesthetic. Pressure from the rider's legs and shifts in body weight, as well as SDs from the reins. The SDs that control human behavior are many and varied, and they arrive via all of the sensory channels. Visual SDs may include arrows, lights, hand signals, as well as much that we read. Auditory SDs include alarms of all sorts, from sirens to foghorns to the rattle of a snake, as well as spoken commands. Sometimes we use tactual SDs, such as a nudge or a kick under the table. And a certain taste or smell may impel us to spit out a mouthful or look for smoke. Various potential stimuli may or may not function as SDs in any given situation. A law-abiding citizen may well go through a stop sign if he's rushing his wife to the hospital. Whether or not a stimulus is an SD depends on such variables as past history of reinforcement and the motivation effective at the time. We have defined a reinforcer as any stimulus that increases the strength of any behavior above its operant level. When the presentation of a stimulus strengthens behavior, the stimulus is called a positive reinforcer. Applesauce has increased the rate of trapeze swinging. The operations for determining whether or not a stimulus is a positive reinforcer consist of measuring the operant level of some response, such as swinging on a trapeze, of presenting the stimulus in question when the response occurs, and of measuring the strength of the response again after it has been followed repeatedly by the stimulus. If response strength has increased, the stimulus is a positive reinforcer. Because of the phenomenon of satiation, we would normally deprive the animal of the stimulus in question before testing its reinforcing properties. Some stimuli acquire the property of reinforcing behavior. Of themselves, they may be nothing but a piece of paper or a scrap of cloth. But through a history of association with reinforcers, they have become conditioned reinforcers, and they can exert a great deal of control over behavior. Among the most powerful of these conditioned reinforcers are the generalized reinforcers, such as praise. Generalized reinforcers are related to a wide range of other reinforcers, which is probably why they are so effective in training.
Good boy. Good boy. That's a good dog. Good boy.
Some stimuli control behavior in a very different way. When presentation of a stimulus decreases the strength of behavior, the stimulus is called a negative reinforcer, or aversive stimulus. Presentation of an aversive stimulus is punishment. A rat will be placed in this box, and lever pressing will be reinforced on a schedule of continuous reinforcement. When he presses the lever, the pilot light will come on, and a pellet of food will fall into the food cup. When he is responding at a stable rate, we will discontinue reinforcement, and lever pressing will produce a brief 300 microamp shock through the grid at the bottom of the cage. The shock is delivered when the pointer moves up to 300 microamps. now. The shock interrupts his lever pressing behavior, but he returns to the lever almost immediately and presses again. The second shock also interrupts his behavior, but again he returns to the lever. The third shock temporarily suppresses his operant behavior and produces the visible respondent behavior of panting. In 15 minutes, he did not resume pressing and was returned to his home cage. Punishment and reinforcement are not opposite ends of a continuum. The effects of reinforcement are pretty much restricted to the response that is being conditioned. Punishment, on the other hand, may have widespread effects on behavior. An aversive stimulus has two major properties. It decreases the strength of a response that produces it, as we have just seen, and it can also increase the strength of a response that removes it. A rat can be trained to press a lever if this response removes an aversive stimulus that is already present. The presentation of an aversive stimulus is called punishment. The removal of an aversive stimulus is called negative reinforcement. In this model, negative reinforcement and punishment are completely different procedures with completely different effects. The operations that define punishment start with measuring the operant level of a response, such as lever pressing. Then, a stimulus, such as electric shock, is presented when lever pressing occurs. If the rate of lever pressing decreases below operant level, the stimulus is aversive, and these operations constitute punishment. To define negative reinforcement, we also start by measuring the operant level of some behavior. Then the stimulus is presented, and its removal is contingent upon the response. When lever pressing occurs, an already present electric shock might be turned off for a period of time, such as 10 seconds. If the rate of lever pressing increases, then the stimulus is aversive, and the operations constitute negative reinforcement. Instead of terminating an aversive stimulus, a response may prevent its occurrence. This behavior is called avoidance behavior because it postpones or avoids the aversive stimulus. The baby rhesus macaque, 3 months old, has been trained to press the lever to avoid a 1.5 milliamp shock. A 1,000 cycle tone precedes the shock by 15 seconds, and a lever pressing response while the tone is on avoids the shock for that trial. The monkey avoids the shock as long as she presses the lever within 15 seconds of the onset of the tone. This procedure, which allows the monkey to avoid all of the potential shocks, does not seem to disrupt her other behavior. This is normal behavior for an infant monkey confined in this small space. She presses the lever in many different ways, all of which operate the microswitch. Therefore, they all may be defined as lever pressing responses. The definitions of reinforcement and punishment are operational. If the presentation of a stimulus strengthens or maintains behavior, then by definition it is a positive reinforcer. If the removal or avoidance of a stimulus strengthens or maintains behavior, it is a negative reinforcer, no matter what the stimulus is. This rat is pressing a lever which causes small electrical stimulations to be delivered to the region of the posterior hypothalamus of his brain. The experimental procedure is called intracranial self-stimulation, or ICS. The electrical stimulus is delivered to the brain through long wire leads whenever the rat presses the lever. The experimenter monitors the electrical stimulus on an oscilloscope. and lever pressing responses are recorded on a cumulative recorder. Electrodes have been permanently implanted in the rat's brain. During an experimental session, the leads are connected to these electrodes at screw terminals attached to the top of the rat's head. This rat is pressing the lever on a schedule of continuous reinforcement. Each reinforcement consists of 1/2 second of electrical stimulation. Since electrical stimulation is dependent upon lever pressing, and since the rate of pressing is maintained way above operant level, the stimulus is, by definition, reinforcer. As you can see from the animal and from the cumulative record of his responding, the lever pressing behavior is very stable and very persistent. It may continue for many thousands of responses. Intracranial self-stimulation provides a technique for investigating functions of the central nervous system, much as histology provides the means of studying the structure of the central nervous system. The reinforcing properties of ICS have now been studied in many species besides the rat, from goldfish to man. The general conclusion is that behavior reinforced by these electric stimuli is quite similar to behavior conditioned and maintained by conventional reinforcers, such as food.